So we've got Ript, a terse but expressive DSL for IP tables happening now. We've got Lindsay Homewood. Lindsay's a sysadmin, developer, toolsmith, engineering manager who lives in the Blue Mountains in New South Wales. He is the creator of Cucumber Nagios, which is a tool that helps you describe how a system should work in natural language and outputs whether it does in the Nagios plugin format. And Visage, a web service and interface for exposing collected statistics. I'll pass it on to Lindsay here.
Thank you very much. Can everyone hear me okay? Awesome. Okay, so today I'm talking about Ript, which is about making Linux firewall change management more resilient and easier. So hi, my name's Lindsay. I'm Oxesis on Twitter. And yeah, like I said, today I'm talking about Ript. So the whole Ript story actually starts all the way back in 2008. Funnily enough, linux.conf.au. So almost exactly 5 years to date. Who here was at LCA in 2008? Cool, okay. Yeah, it's Melbourne, yeah. So at the time I was just finishing up a large desktop Linux deployment for Kennard's Hire, and I was there with a friend, Matt Moore, who's from, at the time was from Bulletproof Networks, now he works at Atlassian, heading up the hosted operations team there. And Matt posed this interesting problem to me. And the scenario is basically Bulletproof, who are doing infrastructure as a service and managed hosting, have lots of multi-tenant firewalls. And there are lots of rules per tenant. So it basically means that all the different customers are on like this sort of horizontally scalable firewall platform. And there was an existing tool that was used to describe what these rules were, but it sort of built the rules in a bit of a dumb way. It was originally built around IP chains, and they sort of reworked it to make it work around IP tables. And fundamentally what this meant from a business perspective is that whenever they were making a change to the firewall rules, it meant that there would be downtime. And what was even worse was that it wasn't actually just downtime for that one customer, it was actually downtime for all customers. That's pretty bad. And on top of that, so yeah, it basically was a situation a bit like this. So it's great if you're that dog, but it sucks if you're the other ones. And what was even worse was the rule application was linear. So basically, as they added more rules to the system, it would get slower. And worse off, if you were provisioned to one of these firewall pairs, at the end of the firewall pair's lifecycle, you would actually get the most downtime. So your rules would be applied linearly. They would always be applied at the end, which meant that you could have up to 2 to 3 minutes of downtime every day, even if that wasn't, if there were changes that were being made on that firewall pair. And it doesn't matter if those changes were for you. They could be for anybody. On top of that, there was a fair lack of expressiveness when describing the firewall rules. I see Pete is nodding his head because you probably used a very early iteration of it.
I did write a big chunk of it, yes. Sorry.
I know who to blame. And it was quite brittle, error-prone. Lots of small changes have been made to it over time, but it wasn't necessarily designed to be sort of a resilient, scalable firewall manipulation tool from the ground up. And one of the big problems with the errors was that it would do very, very little validation of the inputs. So it's very possible to put particular inputs into the way that the rules were meant to be built that would end up taking down the whole firewall pair. So fundamentally what the business was looking for was a tool that would compartmentalize the changes, so making changes for one customer wouldn't affect all the other customers, and preferably these could be done with zero downtime. And on top of that, which is sort of a nice to have, would be a nice friendly language for describing the rules. The previous tool was written in M4, God help us. So the new tool we decided to write it in Ruby. And we wanted shortcuts and validations to sort of dry out the rules so we're not repeating ourselves all the time. So this is an interesting idea. I hacked it up in the car on the way back from Melbourne, sort of like a 10-hour marathon session. And it was a rough prototype produced by the end of it. There was no iptables rule generation. The focus was really on the language. Could we get the level of expressiveness that we wanted and do the validations that we wanted with the DSL that was written in Ruby. And we're fundamentally asking this question, what is the DSL going to look like? What are the users going to be using? The technical internal implementation is like an interesting problem to solve, but the business problem was we just needed something that was easy for the people at the coalface to make changes to the firewalls every day. And yeah, there was a bit of stuff about what the resulting data structures would look like, but that wasn't really the focus. And that's where this name Ript came from. It's just literally just Ruby and iptables. So the questions were answered, the thought experiment was complete, that was it. Fast forward to 2010, 2 years later, I was hired at Bulletproof, completely unrelated to this Ript stuff. But within the first few days of me being there, we had an outage that was caused by some of the problems that I was talking before about the previous firewall tool. And that led to a fairly interesting discussion within the operations team about how we could perhaps improve our tooling overall. So I dragged up some of the demos that I'd done, and the prototypes that I'd done of Ript. And that was really great for planting a seed in people's minds about what the possibilities were. But fundamentally at the time, we had bigger fish to fry, other more pressing business priorities. So it sort of, that was it. It was sort of left there for the time being. So then, March 2011, we actually, so first commit here. And we sort of did this as a Thursday afternoon skunkworks project, so it was just me and another engineer. We were sort of doing it off the books for a couple of hours every Thursday. So this guy here, Steve Fisher, who had a huge amount of organizational knowledge about what Bulletproof was trying to do, and a lot of change management experience as well. And there was me who sort of had the iptables knowledge and the testing experience. So we did a bit more prototyping of the DSL to extend the initial prototype that I put together. And this is an example of what that prototype sort of looked like. And then we tested it. We just tested absolutely everything. We didn't even implement any of the iptable stuff behind the scenes. It was just like, let's test how people are going to be using this. And then we started adding validations and verifications for how the rules were being outputted behind the scenes. We were using an outside-in testing tool, so we're using Cucumber, just to try and communicate what the rules were, what the tool was meant to be doing in a business-friendly language. And then we implemented this concept of migrations, which is actually fairly fundamental to the way that Ript works, and I'll talk about that a little bit later. But fundamentally, for us, it meant that we were able to do zero downtime changes, and this is really, really important to the business. We basically found a way to hack around NetFilter and iptable so that we could do close to zero downtime migrations. And compartmentalizing the changes there, and then we took it live. Fantastic. Now it's actually in use by some of our largest customers, so Whirlpool, which you all know and possibly love, maybe you hate, maybe you're one of those people that DDoSes us occasionally. Movember, Quicksilver, IMAX, Network 10, yeah, we've got lots of really big customers using this. So this is in vaporware. There are tons of people that have been using this for the last year or so. So this is interesting. Tell me more. The language. So let's look at the stuff that we were looking at from a business perspective. Let's making this as easy as possible for people to make firewall changes. So fundamental to Ript is this concept of a petition. And a petition is basically a way of grouping up a series of rules, and they're namespaced as well. So in this particular example here, we've got a petition called Joe Blogs Code. And then within that, we have a bunch of labels and rules. So what are labels and rules? Well, labels are really, really simple. They look something like this. So there's just a method that you call, and it's just a key value pair. So this part here is the key, and this stuff here is just the value. And you can basically, it's a hash, so you can pass whatever arbitrary information you want in there. So those labels are scoped to a petition. And that's really useful because it means that you might be using the same labels across two different petitions here. So we have a consistent naming scheme across all the different services that we provide. We're going to have a conflict there with like app01 in one environment for foobar, and we're going to have another app01 in another environment. But the nice thing about this is that they won't conflict with one another, which is exactly what you want. Okay, so that's labels. Let's have a look at rules. This is the real meat of Ript. So you've got all these labels here we were looking at before. And rules are really simple. So this particular example here is a rewrite rule. So this first bit up here is just a comment. And it's not actually used anywhere else, but it's actually impossible to invoke rewrite without at least passing some text in there. And we make some size validations on that. We don't check that what you're putting in there is semantically correct, but there are other ways to make sure that engineers do that, like having a reasonable process for making firewall changes. And then we have a bunch of arguments to the rule here. So this is just a Ruby block. It's not particularly magic or anything like that. So in this particular example here, we're saying that any traffic that hits joeblogsco.com, which maps to this IP address up here, on port 80 should be sent to apo1 on port 80 as well. Then we can add multiple rewrite rules as well. So that one before was for port 80. This one here is for port 22. So HTTP and SSH. And the default policy behind the scenes is to actually drop the traffic. So if you haven't defined a rule in Ript for allowing some traffic to pass through, it will just drop it, which is a fairly same way of doing firewall management. So when you actually run this is just setting up a DNAT rule, right? Which is going to be on the NAT table in iptables, a net filter. So what you actually need is an accept as well. You're saying, okay, I'm going to rewrite this packet, but you actually need to be able to accept it to go through the filter table so that it will actually be sent to someone. So that would look something like this, right? And you need to add that, except that Ript is really smart. Ript does this for you. It knows the default use cases that you've got. It's aiming for that 80% of the use cases that you have, and it will do those exceptionally well. And it means you don't have to think about implementing this sort of stuff. So yeah, that particular rule set that we've got there is exactly equal to this. And in fact, because of the way that Ript works internally, if you were to say, write this, and then you forget that Ript is smart and doing a lot of this heavy lifting for you, and you were to write, this, what Ript internally would do is it would actually go, oh, okay, when the user defined the rewrite here, I've automatically generated an accept, but I see there's another accept with exactly the same arguments, so I'm just going to remove the second accept. Yes, question?
That says port 22 and that says port 80. Is that just a mistake?
Yes, that is a mistake. My apologies. All right, and that's fundamental to us trying to dry up the rules. We don't want engineers to be repeating themselves all the time. And then there's a bit of cleanup that we can actually do to the examples that we were looking at there. So here you've got this rewrite rule, two rewrite rules actually, going from the same source and same destination, and just different ports here. So what you can actually do is you can just combine the two like this, and it will expand them and generate separate rules, and it'll generate the associated accept rules, it'll do all that smart stuff for you. Then we can start locking these down a bit more as well, so if you need a bit more specificity in your rules. So you see here the two examples again, port 80 and port 22. Let's say we wanted to add a trusted office, because you don't want SSH access open to the world. So all you need to do here is define another label and what that trusted office is, and you define from down here, and it'll increase the specificity of the rule. Ports as well. So there's a multitude of ways of defining ports, and it'll basically, Ript will handle unpacking all the different port definitions and generating rules for each of those things. So the default way is just getting a list of ports. Right here we've got port 22 and port 993. You can do port ranges, which is just using the built-in range data type in Ruby. And Ript is smart behind the scenes because it sees that that's a range, and it'll actually turn it into a 6,000:8000 as iptables would expect, rather than generating 2,000 rules, which a naive implementation would do. Then you've got port mappings as well. So you're saying here that any traffic that comes in on port 80 to joeblogsco.com will be actually sent to port 8080 on apo1. So very simple port mapping rewrites. And then you can actually combine all these different things together as well if you so feel the need. The only caveat is that the port mappings need to be the last argument, and that's sort of a Ruby limitation, but it's relatively easy to keep in mind. So yeah, these need to be last. Then there's protocols as well. So by default, it's actually just using TCP because it's generally the sort of rules that you're doing most of the time. but you can actually specify UDP, and you can also specify the protocol number as well if you wanted to do that. So more rules. So yeah, we've got a drop here for a bad guys. This is useful in a standalone firewall context. So yeah, you just add another label and you've got another rule invocation right there.
So what order does that happen in?
That's a very good question. Technically, behind the scenes, it will actually happen top to bottom. So it's relatively imperative. Generally, you don't need to worry about that, but it is something to keep in mind. That's a very good point.
So in that case, then, bad guy's not going to be denied.
Yep, you're absolutely right. And this is an example.
And I've actually someone's understood that.
Yep, no worries, all good. Yes?
Can you do a not from? So then you wouldn't have to have that second rule, you could just say in your rewrite rule, and not from this guy. So
Yeah, right now the DSL doesn't support that, but we should absolutely add that as a feature. It's a good idea. Any other questions? Yes, go.
Can you add fragments of iptables code that don't fit into this scheme?
Oh, that's a very loaded question. I will not answer it on the video feed. You can come talk to me about it afterwards. The short answer is yes. So yeah, you can also be a bit more open as well. So you can specify a net mask here. So we changed it from bad guy to bad guys, and it'll apply the same thing down here as well with a net mask. One of the other really cool features is that you can just pass this log equals true to any of these rule definitions, and it'll add a corresponding log rule in front of that as well, which is really handy. In fact, it even goes so far as you can add that log equals true all the way up here on petition, and it'll actually cascade down to all the different rules that you define. You can actually negate that as well, so you can do log equals true up here, and then log equals false on, say, just that rule, if you want to do that. So don't repeat yourself is a fundamental thing that we're trying to achieve here. So Ript provides a whole bunch of shortcuts as well for defining things. So if you, rather than defining a whole bunch of different rewrites, you can just pass in a list and it will generate individual rules for each of those things. You can also specify a big long list of froms and tos, and it'll actually unpack that. So this will generate an unwieldy number of rules. And I probably wouldn't recommend doing this, but it shows you the power of what you can actually do with the DSL. So, the rationale. How do we get to here? Why am I talking to you today? So we had this existing tool for describing rules, as I was saying before, but it did things in a dumb way, and it gave us a whole bunch of downtime. This is really, really bad, fundamentally. And what we realized was that the real problem that we had with the previous tool was that it was focused on making large changes. So they weren't in isolation. It was just like if I want to change one rule, I have to regenerate all the rules. This means that fundamentally we had a poor separation of concern. It's sort of like putting everything, like you're doing object-oriented programming and then putting everything in one gigantic method. Right? You wouldn't do that, right? You would tend to split it out into separate, smaller methods so that you can easily refactor and all that jazz. So how do we fix this? We sort of went back to the drawing board here about how we're actually going to do the rule application, because we sort of had the DSL problem solved, but the real crux of the issue was how we could actually apply these rules more cleanly. And fundamentally, the business wanted to increase the frequency of the changes, right? Because you don't want to have to lock down all your changes into a change control window. You want to be able to make them 24 hours a day. And we really wanted to limit the size of them as well, so that if you make a change for a single customer, it doesn't cascade and overflow to all the other customers. And fundamentally, we're just trying to remove friction from the whole change management process. And this is really fundamental when the business is growing at such a quick pace. And you probably noticed that all of those three things here, the increasing the frequency, the limiting the size, and the removing the friction, are just core tenets of what continuous delivery is. So there's nothing particularly magic about what we're doing here. We're just applying the same concepts behind continuous delivery to iptables firewall management. And what we really wanted to do, the end goal, was to actually eliminate change windows so that they're 24/7. We didn't want to have to. We want the changes to be so small that we can make the changes whenever we want, and we don't have to make sure that we alert all of our customers and it's done in a particular time of day. One of the real big problems that you can have is, if you've got the change window between, say, 4 and 6 o'clock, right? And a customer emails in a support request at 3:30 saying, hey, can you please add this firewall change for me? If you didn't have an engineer available to be able to do that, it meant that you'd potentially have a 24-hour lead time before that change would even be implemented. And that's really bad, especially when you move, as an organization, you're moving more towards a 24/7, follow the sun sort of support model. You want to be able to make changes anytime. And that 4 o'clock to 6 o'clock change window, what time zone is that? How does that affect when you've got customers in different time zones? Like it might not, the 4 to 6 o'clock might be fantastic for us here in Australia. But then you've got customers in Europe. That's like the beginning of the day. That's just a dumb time to have a change window. So we want to minimize the impact, minimize the risk of these changes, so that we can deliver more value to the customers. So yeah. Reducing risk, releasing early, releasing often, fundamental things in open source, and we're just applying it here to change management. The other really important thing here is failing fast and recovering quickly. So because the changes are compartmentalized, if you screw up a change for one customer, it's only ever for that one customer, and it's relatively easy to roll those changes back. And again, it's only affecting that one customer. So we sort of went back to the drawing board after doing this introspection and realizing what we were actually trying to achieve at a business level, and we sort of asked ourselves, okay, this is not rocket science. How are other people actually solving this problem in, preferably within IT, but maybe other disciplines within IT? And fundamentally what we were trying to do here is just incrementalism, right? Just making incremental changes to data. So you're asking questions about what the current state is. And you're going from a potentially current and unknown state to some sort of desired state. Hopefully you know what the current state is, but you can't always guarantee that. So we looked at active record migrations. Who here has done a bit of programming in Ruby at all before? Okay, so a couple of people. So active record is just an ORM, which is part of the Rails project. So it's an object relational mapper. It basically it provides a nice Ruby interface to materializing objects out of a database and serializing them back. So this is sort of from the active record migrations documentation. And this is really important. So what we're trying to do here is just describe the transformations, how to get from one state to another. And you want to be able to execute that in multiple environments, or in this particular case, multiple databases that might be 1, 2, 5, 10 versions behind. So this is a fairly close analogy to the way that we technically wanted to try and solve the problem. So if you look at an example here of an active record migration, it's really, really simple. You have an up method and you have a down method. The up method adds a column, the down method removes a column. Pretty simple and straightforward. I use another ORM, and so it's got a much more sort of Ruby-like DSL type syntax. So you notice that there's a bit of crossover there with the Ript DSL for describing things. So very similar sort of thing, right? What this thing is doing here is sort of fairly analogous to what this thing here is doing. But the cool thing about the SQL migrations, which are now actually in the active record migrations, is this. So you can just go to change. And it's smart enough to work out that if I want to create a table with this primary key in this column, obviously to go back to the previous version, then just do the opposite, just drop the table. Pretty simple and straightforward. And that's how simple we wanted to try and make the rule application in Ript. So in an active record or a SQL world, you basically have a list of migrations here. So you've got one migration that's basically incrementally changing the state. We took a slightly different approach with Ript, which is that we're always defining the current state, what we want the firewall rules to look like, but then we let the tool do all the heavy lifting to work out how to get from where you currently were, that sort of unknown state, to where we want to be. And yeah, in SQL it's really simple. You just run the migrations, point it at a database, that's it. That's fundamentally what we were trying to get to, that ease of use, that sort of workflow. So show me, this is all fantastic, but let's actually have a look at it. So I'm on a firewall machine here, it's just on my local laptop. So I've got a ript.lca directory, and there are two files in here. There's well technically three if you include doc.git. There's bootstrap.rb and a linux.conf.au. So bootstrap.rb has these raw rules that you were asking, sir, up at the back about before. This is evil and this is going to go away. but it's the necessary stuff required to get netfilter into a state where Ript can do the incremental changes on top of it. So generally, you'll put this in place in your project, and you'll never touch it again. And just forget that there's such things as raw rules. They are evil. So if we have a look at Linux or conf.au. So here we're saying that we've got this label of Linux or conf.au with these particular addresses here. We've got an apo1, an apo2, and an app subnet behind the scenes. We've got a rewrite for the public website. So we're saying that any traffic that goes to port 80 on Linux or conf.au, which is this .2 address, DNAT it to apo1, and also rewrite the port to port 8000. That's a fairly sort of standard practice for sandboxing apps as well. You preferably don't want to give them root level access to be able to bind to a port below 1024. So this is a fairly common pattern. We've got a outbound SNAT rule here saying that any traffic originating from within that subnet should be SNATed back out. And we've got an accept rule here so that I can access this machine repeatedly. Okay, so if I'm going to run Ript, I go ript rules generate ript.lca. Okay, and what this has done is this has passed all those files in there, and it has outputted a series of iptables commands to do what we want. The cool thing about Ript is that it's actually recursive. So if I run ript generate here, and then I run, say, ript rules diff. It's not going to give me a good example. Let me change something here. Let's say we do port 25 as well. Okay, now I do ript rules diff. So what ript rules diff does is it analyzes the output of iptables -l and a couple of other little options in there. It works out that the hash of the rules that I want is different from the hash of the rules that's loaded into the kernel. Therefore, it generates, it basically outputs all the different rules that it would need to apply to get to the state that we want it to be in. So I've just done this diff. It hasn't actually applied anything, but the cool thing behind the scenes is that it's actually run ript rules generate and then compared that to what's in the kernel. So running ript rules diff and ript rules apply, which I'm about to run, ript rules apply will call ript rules diff will actually call ript rules generate. So we know that it's internally consistent top to bottom. So now, if I want to do ript rules apply, it's going to output the rules here, and I do the diff again. There you go, magic. So it's idempotent. It knows that we're up to the correct desired state. Fantastic. Okay, so that looks pretty sweet, but how is it actually working behind the scenes? The meaty technical detail that I know you're all here for. So, iptables. It uses iptables. Let's very, very briefly recap what the different tables are on iptables and the different chains. So you've got a filter table here, and you've got an input, forward, and output chain. So you can all read the slides here. But it's basically for stuff that's being, packets that are being delivered or originating locally, or in the forward case, stuff that's being forwarded someplace else. Then you've got the NAT table, and then to vastly simplify what the pre-routing and the post-routing chains do, there's packets for DNAT and packets for SNAT. That's certainly the way, the model that Ript uses internally for sort of dealing with iptables. So, Ript has a bunch of Ript-specific chains that it uses to apply the rules on top of and remove the previous rules. So we have this for a chain. And this is for traffic scrubbing, so it's actually what was in that raw rules definition before. So we do things like, allowing ICMP, stateful packet inspection, keep alive COMMARK if you're using sort of a HA setup with keep alive there. And this is a boilerplate chain. Like I said before, you are never, ever going to need to touch this. And then we have a partition A chain. And this is a pointer. It basically consists of a series of pointers to partition access changes. So your input, output, and forward chains are all going to jump into the partition A chain, and then they're going to jump back out again. And then you have a customer-specific or a petition-specific chain. So in this particular example, we have a petition named moport.au. And there's a couple of different parts of this name here. So you've got the actual petition name, as you would find in the Ript DSL. Then you have a rule set type, so A for access, D for DNAT, S for SNAT. and then you have a hash. And that hash is basically calculated by generating all the rules, concatenating them all together and taking an MD5 sum of it. So it's relatively simple and straightforward. Okay, so how does all this chain traversal stuff work? We talked about before A and petition A. Let's have a look at how a packet would actually go from top to bottom. So a packet will come into either the input forward or output chains. It's all going to bounce into this before A chain. From there, it's going to bounce back out to the input forward or output chain. And then it's going to go to petition A. So this is where all the customer specific chains are, or these petition chains are. So from within petition A, you'll have a bunch of petitions that you've got defined here. And the packet will try and match these different pointer rules that you've got. So it'll go into each of these here. And let's say it doesn't match any of these pointer rules. It jumps back out again into input forward or output. And that's it. Okay, so we have this concept of a pointer. A pointer lives in the petition, in a petition chain, and they're very, very, very lightweight. And all they do is they basically match on very high level parameters, and they will jump into a petition specific chain. So there's pointers for each of the destinations and technically for each of the sources as well. So rather than doing sort of, looking at all the different fields on the packet, we're just looking at two things, the source and the destination. And assuming that you have nice network segregation between services, it'll be relatively easy to do. So the pointers match on the source and destination. And it means that we have very, very quick traversal of petition A. One of the problems we've had with the previous system is that if you have just lots and lots of rules, the more rules that you add, if you've got rules that are at the very, very bottom of that, they're going to have to try and match all the other rules in front of that. So we want to make traversal of petition A as quick as possible. So in this particular example here, you're going to go into this particular petition chain, doesn't match. Sorry, you're going to try and match against this pointer. This pointer doesn't match. Doesn't match against this pointer, doesn't match against this pointer, gets to this pointer here. Okay, so we've matched on this particular pointer rule. It's probably a series of pointer rules, but let's just say it's a single pointer rule. And from here, we're actually jumping into the petition chain itself. So then we do what's called in iptables and netfilter a verdict rule. And that's things like logging, accepting, rejecting, dropping, all that jazz. And we're going to go from within that partition chain, we're going to try and match all these different rules that are in here. And this is where all the specificity comes in. This has all the meat. So we're going to try and match on this rule, doesn't happen. Okay, it matches on this reject here. And from here it's a verdict rule, so the packet gets rejected and that's it. If a packet didn't match any of these things, it would actually jump back out again and hit the bottom. And there wouldn't be any matches. And of course the default policy is to drop, so nothing would actually happen to that packet. So logging is a little bit of a special case in iptables. So logging rules are technically verdict rules, except that they allow you to continue. So they're not really a verdict, they're like a pseudo-verdict. So in this particular example here, you've got a log rule, which is matching on this .72 here, right? Notice that it's got exactly the same address as this accept here, so it's going to log, and so it's matching this verdict, and then it's going to skip, and it's going to go to the accept, okay? And that's it. So that's basically the way that the logging rules work in all of this as well. So this is the way this is the design that Ript uses to allow zero downtime migrations. So when you run a Ript rules apply, all that's doing is it's inserting new rules to the top of this petition chain. Magic. And Ript rules apply always inserts pointers at the top of the chain, never at the bottom. So if you're making lots of changes for a particular customer or on a particular petition, they're always going to be inserted up at the top. Now, there's a little bit of a problem here because we've actually got overlapping pointers. We've got pointers for the same customer here. Slightly different hashes though. So what happens in this particular context? Well, this is a bit of a tricky problem because you've matched on this particular pointer, you've jumped into this petition chain, this customer petition chain, and you don't actually match on any of these verdict rules. So like I said before, you jump back out of it. So there's no match, it returns back to the petition A chain. But you've got this other pointer rule that points to this old chain from when I defined the state however many iterations ago. And the problem here is that because it has the same destination and it jumps into the old chain, you can actually hit old rules. So you don't actually have a clean state, right? That's actually a pretty bad situation because you might not want this accept to actually happen anymore. So you need to clean the old rules. Unfortunately, Ript makes this exceptionally simple for you to do. So you literally run ript clean apply. There's also a ript clean diff as well, if you want to know what it's about to do. But again, it works just like ript rules apply as well. It's recursive all the way down. So what happens when you run a ript clean apply? Well, just this. It notices that there's an identical partition name, so it blows it away. And oh look, there's another identical partition name. There we go.
Why don't you do that by default?
That's a really, really good question. So we took the approach that it would be it'd be easier to make the operations simple and atomic, and it's up to the operator to add the orchestration on top of that. So in the way that we actually do stuff with our workflows, that happens automatically. From a user's perspective, they don't know about it, but we wanted to separate it out as much as possible. So workflows, how do we actually use this? Well, primarily we recommend that you store the rules in Git and use config management to actually make sure that Ript is installed on the machine. So how does that actually work? Well, in the bulletproof context, we use Puppet to install Ript on a machine, but you could very easily use Chef or Ansible or any of those other new hotness. Then we have a ript.rules repo, which we actually deploy with Capistrano. We treat it like a web application that we're about to deploy a new version of. So that's deployed here into this etc firewall current directory. We just do a cap deploy. Now by default, when you do a cap deploy, it's actually running ript rules diff. It's not actually applying anything. The operator specifically needs to do apply equals true for those rules to be applied. And funnily enough, runs ript rules apply. We also are starting to do more development around Vagrant. In fact, the demo that I was using just before is all built on top of Vagrant. It's going to be open source this week as well. So there are a couple of challenges in writing this sort of tool. So testing, fundamentally, is a bit of a difficult problem. So we're using Cucumber, which is nice and high level and outside in. And we have tons and tons and tons of examples of how to use the DSL that is shipped with Ript. And not only that, they're actually used by the tests. So they're not just abstract examples that are never up to date. We use those examples to run the tests, which is pretty fantastic. So yeah, we ship 41 different examples right now, and that's ever increasing. Ript is sort of complicated because it's sort of like system code, but it's not quite. It's sort of systems management code. You have problems with lingering state as well. So if you are hacking on the tool and then you make some sort of error in your logic, you could potentially end up with the system in a broken state where you can't actually get into it anymore because you've applied some rules that will firewall you out. That's bad. So we have this rake clean slate task. And we actually call that at the end of every test run. So even if you manage to run a bunch of tests and execute some code that is broken and leaves the system in a broken state, after about 10 seconds you'll be able to get back in again, which is pretty useful. Open sourcing. This is a bit of an interesting problem for us. So fundamentally we love open source. We're using it everywhere. But we were focused on building this minimum viable products to get something out the door so that we could actually improve the process and not feel the pain operationally. So we started very, very concrete in the way that we were writing our examples. And there were some hard-coded bulletproofisms in there. And what that meant is that when it came to open sourcing, we needed to scrub a lot of the internal references from our tests. And this meant that we basically had to go back and rewrite the whole history of the tree to be able to do that and keep that consistent. And this is a horrible, horrible, horrible problem. So much so that we actually just gave up on it entirely. We actually ended up just having to nuke the Git repo. So if you look at ript.history, which is an internal private bulletproof repo, we have 234 commits to that. The public repo has 5. Sorry about that. The good news is though that we have a change log, so you can at least go back and have a rough idea where a regression might have been introduced. So all the development from now on is actually happening out in the open though, which is awesome. The only other little sort of crappy bit about Ript right now is the interface itself, binript. It's a little bit manky. It's not using sort of a lot of the newer, nicer ways of writing reusable commands with nested subcommands, but that's something that we're actively working on. And IPv6 as well. Right now has 0 IPv6 support. That really, really sucks. and it's massively important to the business. We're focusing on that quite hard this year. So internally within the API, we call .to iptables on a rule. So for us, adding IP6 tables support will literally be this simple. So it'll just be a flag that says, hey, this stuff is in IP6 tables, and it will, we just need to implement this. So it'll be relatively simple and straightforward for us. Obviously, concepts like NAT don't make any sense whatsoever in an IPv6 world. So it'll actually make Ript a hell of a lot simpler overall as well. And we're expecting that to be sort of delivered around Q2 2013. So fundamentally, this talk is actually about writing our own history, writing our own tools to scratch our own itches. We found that it's very, very easy to complain about all this operational mank that's been built up over a decade of the company existing. And we really needed to fundamentally question our circumstances about the problems that we were actually trying to solve. The tool, when it was written, absolutely fantastic. It really did a fantastic job and it carried the business a hell of a long way. But the circumstances fundamentally have changed, and that's why we needed to reevaluate what the problem is that we're trying to solve. So if we're working with shitty tools, then what's the thing that led us to this point? Well, in our particular case, we're just growing so quickly, so we needed a better tool that would handle that sort of scalability. It's a relatively simple question to ask and answer, but lots of people just sort of forget to do that. So yeah, what's the problem that you're trying to solve? For us, the tools are a means. They can be rebuilt, rewritten, replaced. Whereas for us, it was about finding our concrete principles, which was frequency, size, and reducing friction. Thank you very much. Questions?
I'm hoping I've missed something really simple here, but why not iptables restore and save?
That's another way of applying the rules. So the simple way that we wanted to implement it was to just output a bunch of shell commands that you could, in theory, just run manually as well. To add iptables save and restore support would literally be as simple as adding like the IPv6 support. The nice thing about the iptable save and restore stuff is that you can also do it incrementally, which is going to save a lot in the execution time, so that's fantastic.
That's only on the chain basis, though, isn't it?
That's right, and that in a Ript model, that works absolutely fantastic. So, obviously, you're not going to be able to do that with updating a pointer rule, right? Because you're going to need to be able to, you're going to have to dump out all of petition A and load a new one in, and that's sort of bad. So, cool. Any other questions? One up here. I can just repeat it if you want.
I used to run, the system wasn't big, but I just had a script and it would flush everything out and rewrite the rules, and we didn't have any downtime, as far as I could tell.
So there's a difference between actual downtime and perceived downtime. Probably what you were getting in your case was that you had the established stuff set on for the connection tracking. So yeah, provided that you dump, so that you flush only specific chains, you can do that. I know that with Shorewall you can do very similar sort of things to what Ript does. Because Ript is designed from the ground up to allow zero downtime migration. So I'm not in any way saying that what we've done with iptables is unique and you can't do it with other tools. Ript just fundamentally makes it a lot easier than doing it with other tools and writing stuff yourself.
Thank you for your speech. Here's a small gift from LCA organisers and Linux Australia to thank you for your time.
Thank you.